The first example we will examine here of synchronization effect in the animal kingdom is also the most common and easy to find, an ant hive. Ants and bees both form swarms, and both are insect monarchies, with all antennae plugged into one wavelength, the good of the queen of their colony. But ants exhibit another specific skill that bees seemingly lack, the ability to cooperate with one another so efficiently that they can form natural bridges and even natural rafts out of their own bodies in order to support on their backs the more important drone workers, the queen, and the larva. Using their exoskeletons for tensegrity, a colony of ants can natural raft upon the surface of the water in a flood, each ant locking legs with its neighbor and all holding on together to weather the storm. Each ant benefits from their cooperation with all the rest by surviving. For ants, with their hive mind, synchronization of efforts between individuals is not so impressive. Ants and bees, however, are not the only insects that form or travel in swarms. Certain aphids, locusts, and beetles appear only occasionally, en masse, and during these breeding seasons may invade a populated area, posing a problem for the people and plants living there. Mayflies, for example, are small, mostly harmless pests that breed, as their name indicates, during the month of May. They can be seen swarming in a large, dark cloud. As they are all riding the same air current, all the bugs are carried about on its winds, but they use their wings to stay in tandem with one another in order to maintain their formation as a swarm. Whether the mayflies are communicating with one another, as do ants and bees via their antennae, has not yet been thoroughly researched. However, the preponderance of pests traveling in swarms is a matter of no historical debate. Simply because one link on the food chain mimics a certain pattern does not always mean other links in the food chain will as well, although in this case the swarming of pests could explain the swarming of larger-brained species in the animal kingdom. Underwater, we find many schools of fish will form swarms. Although apparently in a feeding frenzy, each fish is nevertheless, theoretically, as independent from all the rest during such mad rushes into cyclonic swarms as they are at any other time when not engaging in such a massive writhing throng. Here one must also pause to wonder to what extent the fish, swimming in a self-connecting cyclical pattern, are influencing the currents of the water they are swimming on themselves, creating a recursive feedback loop, multiplying the force exerted from the fish swimming by the momentum of the current stirred up in the water from them doing so. In the skies, we find many flocks of birds that will form swarms under the proper conditions. These starlings, filmed near Netivot, occupied Palestine, are exhibiting an aspect of such swarming called murmuration, when all the starlings in the flock pivot, dive, and soar in sync to one another, and seem to all be moving as one. And so we see that bugs, fish, and birds all occasionally form swarms, and when they travel about in such a manner, they exhibit a form of synchronization effect. But herein lies the difference between apparently synchronized behaviors being exhibited by living systems and apparently synchronous events occurring concurrently between multiple inanimate objects. For living beasts, their swarming ends whenever they all choose it to, and each breaks off to their own separate way. But for inanimate objects in synchronized conditions, only by changing these conditions can the pattern be broken and the objects become asynchronous again. While we may be able to make a model using Janus colloids that demonstrates a hypothesis about synchronization's role in self-organization, we cannot posit with certainty that this is in any way similar to how atoms form covalent bonded molecules. Even though the model using Janus colloids may appear a convincing replica of how atoms bond to form molecules. It remains dependent on the parameters affecting its confined, closed system of space primarily, and only secondarily relates to anything else beyond this in nature. For example, in the clock's model for Huygens' synchronization effect, the metronomes, if removed from their shared surface, or if the shared surface is removed from its condition of independent mobility relative to the ground, will quickly fall out of phase with one another and revert to independent rhythms. Changing the parameters of the experiment only slightly terminates its effectiveness as a demonstration for the phenomenon of synchronization. Likewise, in the experiment with the two tuning forks, if the pitch is altered in the second tuning fork by applying a weighted clamp, the tone from the first tuning fork will not be able to transfer into the second tuning fork. When two tuning forks with different pitch are played concurrently, their wavelengths still resonate with one another, but they do so in an alternating, phase-shifting tempo, forming an isochronic tone between their combined wavelengths, comprised itself of the difference between these wavelengths. The last model we will examine here is, once again, the model of 15 unequal pendulums, all swung in unison. In this viewing, let us also consider a coded program translating the motions into MIDI-tone musical notes. As we can see, these pendulums sometimes align and sometimes fall out of sync from one another, digressing into more or less randomized chaos one moment, and then forming exquisite optical illusory patterns the next. We can also consider the notes attached to it as forming a melody created solely by classical physics.